Good afternoon, ladies and gentlemen. Welcome back. My name is Mr. Chen. This is MCR3U. Today's lesson, we're going to do hopefully a quick lesson on graphing exponential functions, and it should be pretty straightforward, pretty easy. If you look at the handouts that was given to you, there's a lot of things that are going through there. And in the past, we used to use graphing calculators and graphing programs, but because we're learning from home, I think you can figure it out as we go through it. So I do recommend you have Desmos or GeoGebra, or use your resources from your textbook or the CEMC resources to help you out to understand the graphing exponential functions. And this is our last one. I mean, if we've been talking about parabolas and cubic functions and absolute value, and then we talked about sinusoidal functions, this is our last one, right? So I think you'll find this one not too bad. In some sense, this is one of the more particular graphing. So just take a quick look at what I have on the whiteboard. What you see is the generic function. Just remember the A stands for vertical stretch compression. And if it's negative, it reflects across the x-axis. B is the horizontal stretch of compression. And of course, if that's negative, it's a reflection across the y-axis. C is the horizontal translation. And D is the vertical shift, the vertical translation, up and down. So let's just say we have a particular function, and it's going to be exponential. So how did we do this before? Well, we did a table of values, and notice this is y equals 2 to the x. And notice the unknown is the exponent. I think you guys figured this out. You should have still some conversations about, of y equals x squared. This looks very similar, and this is, of course, a quadratic. So y equals 2 to the x, they're related. Seriously, they're related. But y equals 2 to the x, that's how you say this exponential function. If we do a table of values right here, and I apologize, my handwriting is horrible today. I can actually go with these values. Now you don't have to go through those all 7 those values. When y equals 2 to the negative 3, believe it or not, that actually is 1 over 8. So it's a very small number. When x is negative 2 and plug it into y equals 2 to the x, that is 1 over 4. When x is negative 1 and plug in y equals 2 to the x, that is 1 over 2. Using our exponent rules, now these ones are a little bit easier. A lot of you should already know the negative exponents are fractions because we learned that. When x is 0, that's going to be 1. When x is 1, that's going to be 2. When x is 2, that's going to be 4. And finally, when x is 3, it's going to be 8. Now, a pattern that some of you should notice that this seems to be a doubling pattern, right? It seems to be doubling. If we started from 1, we keep on doubling, keeps on going. So that's our table of values. And the generic form for exponential seems to be written like this. Y equals, I'm going to use Z, even though in your package it's a different letter, Z to the X. Okay, so this is the generic form that I'm going to teach you. You might see different bases. Sometimes they use B. I just don't want you to get confused with the B that we have up here. So I don't want you to get confused. So no confusion. So I'm going to be sketching for you really quickly what you're going to notice for this particular graph, y equals 2 to the x. And if you have a graph like that, if you plot those values out, and again, hopefully you actually have some graph paper. That's a pretty good scale. I think some of you are noticing a problem here. -3, well, that's going to be a small point. -2, that's going to be a small point. -1, that's a small point. 0 and 1 is going to be a big point. That 1 and 2 is going to be there. 2 and 4 way up there. And 3 and 8 way maybe up here. And if we graph this going, it's going to look something like that. So this is an exponential growth graph. So it doesn't look like a parabola at all. I mean, if you only saw the domain from 0 to 3, it could look parabolic, but it doesn't. And there's a couple of only key features here for this y equals 2 to the x, right? So let me just emphasize this maybe with different colors so you don't see it. And here are some key features. Number one, it definitely has a y-intercept, and it happens to be 0, 1. Not always, but for this one it is 0, 1, right? What else do you notice? We don't have any observations. It's not like a sinusoidal function. It's not like a parabola. Certainly not like a cubic. So in some sense, this is the hardest one. That's why I still prove with the table of values, but we're going to hopefully understand how the transformation method actually works for this particular function. The second other feature, and I know it's going to seem weird, I'll use pink, is that you might actually know what I'm doing if I draw this pink line here. Well, believe it or not, this is a horizontal asymptote. You've heard of this word before. Recall, you've seen this before for the graph y equals 1 over x. So this is a horizontal asymptote. It means, not saying it will never, but this function, this exponential graph, tries to approach the x-axis but doesn't really touch it. Okay, now it can pass it, but this horizontal asymptote, you can kind of think of it again as a barrier that prevents it from crossing over. So this function has no x-intercept. Again, just noticing some things. Notice I didn't write anything out other than the two things that you see, that this has a y-intercept and it sort of has a horizontal asymptote. And this one's a growth. So hopefully that wasn't jarring for you at all, ladies and gentlemen. Now we're going to continue by graphing another base function, but this time we're going to look at y equals half to the x. And hopefully you notice I used green to show that. As always, let's do a table of values really, really quickly. And for some of you, you might again find this weird to do. Hopefully you're doing it with me. We're pausing the video to help you understand it. Now y equals half to the x. Notice I'm trying to show you a relationship between y equals 2 to the x. Well, y equals half to the negative 3, believe it or not, is actually 8. And then it's 4. And then it's 2. And then look at that. Hey, it's 1. And then half to the 1, it's a half, a quarter, and an eighth. So if we were to graph this, negative 3 and 8 way up here, negative 2 and 4 over here, negative 1 and 2 right there. There's 0 and 1, and then 1 and a half, and then 2 and a quarter, and then 3 and then 8. So hopefully you're going to draw the line of best fit, just like how we did in the first one. I didn't say that, but I think you guys knew what I was doing. And this graph is also exponential, right? Except maybe some of you would call this a decline. Well, this is known actually as a decay. This is pattern actually, some of you might understand this. This is known actually as called halving or half-life. There's a reason why we'll talk about it in a moment. But same thing, just like we had in our exponential growth, this one has a y-intercept of 0, 1. And again, let's write in pink, it seems to have a horizontal asymptote of y equals 0. So those are the only two kind of features that we have. Hopefully you also notice something interesting. Now, I'm going to just hopefully, I didn't get a chance to draw it again, so I have to redo the y equals 2 to the x. And I'll just sketch it out. So this is y equals 2 to the x, and in green, y equals half to the x. Anyone notice anything interesting about these two graphs? I think mostly we would come to the conclusion that they look alike and they seem to be reflections of each other across the y-axis. And some of you actually already know that this y equals half to the x can actually be rewritten as y equals 2 to the negative 1 all to the x, or really y equals 2 to the negative x. So some of you are slowly understanding certain things, and let's just clear this off. I wrote the generic form of an exponential function as y equals a bracket z, where z is the base, all to the b times x minus c plus d. And so I'm trying to keep it the same format that we've been taught ever since our transformation unit, where a, b, c, and d corresponds to what we showed with the generic formula of the transformation function unit. Also with the same with the sinusoidal function. That's why I'm trying to keep it consistent so that everything is fine. So let's just say we have this function, y equals negative 2 in brackets 3 to the x plus 1 minus 4. A lot of things are going on with this hard question that I just threw at you right now. But if you look to the package, I think you can follow along how Dr. Chan and how normally I would walk you through it on what transformations are occurring. I think everyone agrees, and I'll point them out hopefully and highlight them. This negative probably is an A, so this means a reflection across the x-axis. This 2, notice it's not in the brackets. It's also probably an A, and it's probably a vertical stretch by a factor of 2. Notice the z value that I chose for us, for some reason, is 3. Now, although we looked at doubling and halving, notice that this z value is greater than 1. So clearly, if z is greater than 1, it's probably going to be a growth. More importantly, this one's probably a tripling. This one is actually easier to understand because it's a 3 value. The b value is 1, so we don't have to worry about that. This plus 1, though, is probably the c value. And it probably means a horizontal shift left 1 unit. Finally, this minus 4 is probably a d value. It's a vertical shift down 4 units. But what are we talking about? What is the parent function? So let's write that out. The parent function, which is the z value, is 3 to the x. And if you were to draw a table of values for this really quickly, I think you'd be able to do it no problem. Y equals 3 to the x probably would be, well, that's 1, that's 3, that's 9, so that's 1/3, that's 1/9. I think you know how fast we're getting it. And the sketch of the graph, really quickly, it's going to look almost identical to the graph that we did before. Notice this is for y equals 3 to the x. So what would this graph look like? I unfortunately didn't give myself enough room. So I'll do it over here if that's okay, to the left. Well, according to the instructions, reflect across the x-axis and a vertical stretch. So the horizontal asymptote is not going to be affected by any stretches or compressions by the a or b value, or even any horizontal shifting. So that pink line that we're going to draw is probably only be affected by that green vertical shift. But I'm digressing here. I'm jumping the gun. So let's try to do this again. So we're going to reflect and stretch. So this graph right now that we see for y equals 3 to the x is kind of going upwards. It should be going downwards, right? And 0, 1 times by -2 is -2. So -2 is going to be our new kind of understanding here. But we got to be careful with this. So let's just do this in stages. So this one is probably going to be something like this. So this is y equals -2, 3 to the x. Now let's deal with that horizontal shift. So everything should shift left 1 unit. So I know this point is at -2. It should shift left 1 unit. So going left, that should be -1. So that new point should be there. We don't really know what the y-intercept is, but who cares? We're just going to try to get it across. And that's why, unfortunately, these graphs look kind of weird. So the yellow one that I have is y equals -2, 3 to the x plus 1, because everything shifted 1 unit to the left. That unit went over 1, et cetera, et cetera. Now we got to shift it all the way down, and I got to give myself enough room. So I think you're going to be okay. Let's just pause the video for a second as I fix this up a little bit. So I just moved the graph up just a little bit so it's a little bit cleaner. And so some things actually happened so that you can see it a little bit better. I actually shifted that horizontal asymptote from y equals 3 to the x down 4 units to y equals -4. And I still plotted that yellow point at -1 and -2, 4 units down to that -6 there. So it's still going to look something like that. Oops. And it's still going to cut through that y-axis there. And let me just erase some of the stuff that's getting a little messy. So let's just get rid of the yellow one. I'll rewrite the yellow one just so that some people can see it a bit better. The yellow one was the transformations of y equals -2, 3 to the x plus 1, so shift to left. And the green one, which is our final one, y equals -2, 3 to the x plus 1 minus 4. Now, with sketches, it's going to be kind of messy. I do recommend if you check with Desmos or GeoGebra, it might help you out there. But hopefully you figure out, I'm trying to combine all the transformations so that you can physically go through it yourself when you're working through that package. Hope that was helpful. As always, if you need some help, feel free to email me, ask me more questions. Definitely look at the CEMC resources at your disposal. Have a nice day.